Now let's look at the period of these graphs. Now the length of the smallest repeating unit is the definition of the period. So y equals sine x and y equals cos x have a period of 2 pi. That's because every 360 degrees, or 2 pi, they repeat on top of themselves. And we know that for y equals tan x, it's only half that. It has a period of pi. So a horizontal dilation, we've already seen this, with a factor a means that you're going to be stretching or compressing this way. So that means you're going to be changing the x value, and you're going to be virtually replacing x with x over whatever that factor might be. We've seen already that when our factor is a fraction, it compresses the graph, and when our factor is a large number, 2, 3, 4, etc., it stretches the graph. So let's think about replacing x with x over a for each of these graphs, and we get something that looks like this. Now you'll notice straight away I haven't written a here, I've written n. And that's because if we're going to make dilations going this way and this way, it'll be confusing if we've got a's everywhere talking about the same factor. So for period, we generally call the factor n. So we've got x over n in each of these cases. Now this means a horizontal dilation with a factor n. But this formula, it looks a little bit clunky, doesn't it, to have a fraction like that sitting in your formula. So mathematicians generally like things tidy, and somebody at some point must have said, this looks a bit messy, let's remember it a different way. So instead the convention is not to write it this way, but that's a good way to explain it, but to instead write it this way. And we do it this way simply because it looks nice and neat with no fractions in the formula. Now, if y equals sine of nx, what we've done there is we've said, well, if n has to be positive, what on earth is the scale factor here? Now, think through this section. If I had x over n, but n was actually a fraction, it would look like this, wouldn't it? And if you've got something and you divide by a fraction, that's the same as doing x divided by 1 over n, or x times, we flip that upside down, n over 1. So what we get then is the realisation that this situation gives us nx. So if we're going to write this as nx purely to be tidy, that's fine, but what we need to remember is that here the scale factor is not actually n. The scale factor would actually be here, 1 over n. So here I've written where these graphs have been dilated by factor 1 over n. And that's a really important distinction to make. If you're writing it this way, then you've dilated by a factor of 1 over n. So these graphs are actually compressed then. If we had, say, y equals sine 2x, where n was a whole number, what we'd really be saying then is we've got a scale factor of half, and we would have squished it together like that. So this is going to affect their period, isn't it? If we squish a graph together like that, let's say we have something like, let's do an example here, y equals sine of 2x, then that means that we have a horizontal dilation with a factor 1 over whatever that number is, so in this case, half. And that tells me I've squished it together to make it half as spacious, I suppose. So instead of having a period of 2 pi, it's going to use half the space of that to do one full rotation. It's only going to take pi. So as I go to draw this then, you can think about what the normal y equals sine x would look like. It would take 2 pi to get all the way through its complete curve. If we've squinched it up tighter, it's actually going to do that in half the space, and it's going to do it every pi. And the new period here means I can halve it to find pi on 2 will be here, halve that to find pi on 4 will be this, and halve this and find that I've got 3 pi on 4 in here. So that's a nice simple way then of drawing this. Now, if this seems a little bit confusing, you've got a great backup here. All you need to do is think, well, when x is something, what would y be? And just sub in a couple of points to make sure you're compressing or dilating the right way. You'll also get the hang of knowing that a large number here compresses and a fraction would stretch it out. Now if I just sub in pi on 4 here, then pi on 4 times 2 is pi on 2. And I know that the sine of pi on 2, or 90 degrees, is 1. So when x equals pi on 4, sure enough, I get 1. And that tells me that I'm on the right track here and that I must have drawn it correctly. Now, if we are going to draw something like y equals tan of x, obviously we've seen that tan has a different period. Its period's only pi. So I've written down the bottom here, this means that the period is actually 2 pi over n for the sine and the cos curves, and pi over n for tan. Let's think about why. Well, our example just saw that putting a number 2 in here actually squinched up our y equals sine x curve and made it take up half the space. So instead of having a period of 2 pi, it would be 2 pi divided by whatever that number is. So let's go up here and revisit these notes and add to them. And you might want to do this in red pen or something like that to show that we've thought this through. It's 2 pi divided by n, or for y equals tan of x, it's going to be pi over n. And we need to qualify with our statement here of 2 pi over n, or pi over n, that what we're thinking about is where n is this number that is beside the x. So that's relevant there. Okay, now 2 examples. We're going to graph both of these functions, and both of them contain some sort of deviation in their amplitude and period, and we need to look at how we can do that. Now I start both of these by thinking about what the amplitude is going to be and what the period is going to be. So starting on this one, you can put brackets here, or you might see it without brackets. Okay, and this is in the form y is equal to a sine of nx. And what we've actually seen here is that n is not a scale factor. The scale factor is actually 1 over n. But the easiest way to deal with this part, which affects the period, is to say that I know that with sine and cos curves, the period is 2 pi over that number. So rather than thinking about a scale factor, which nobody's mentioned in this question, they've just asked us to graph it, I know that this will be 2 pi over whatever is here, and in this case it's a 2. Now 2 pi over 2 is just pi, so that's the period of my graph. And the amplitude, that is actually a scale factor. It's been stretched by a factor of 5, and it's the number that's sitting out the front here. So I can see that I've got an amplitude of 5. Now I like to sketch something like this by just doing a tiny little sort of mud map sketch showing what I'm thinking, so that then when I go to do my good one I can get it looking nice. I know that y equals sine of x starts at the origin, it goes up first then down, and it takes 2 pi to get all of that first cycle done. It also toggles between 1 and minus 1. But if I'm stretching it out to an amplitude of 5, it's going to look much more like this, where it's going up to 5 and it's going down to minus 5. And if the period is pi instead of 2 pi, this point out here won't be 2 pi anymore, it will just be pi. So just by doing a quick sketch like that, now I could draw up a nice one and think about getting it sort of roughly to scale, if that's important to you. It doesn't really have to be to scale, but if this is 5, and I know pi is about 3, then if we're going up to 5 and we're going down to minus 5 here, then 3 is only going to be out here somewhere. So I've got pi, I'm going to need pi on 2, and I'm going to need to find pi on 4 and 3 pi on 4, because I know that in my graph, my points of interest are the start, the halfway point, and then my top point is a quarter of the way, and my bottom point is 3/4 of the way along the cycle. So that way I can think, well, I'm going to start here, and then I'm going to go up, I'm going to go down, and then I'm going to go all the way down, and then back up again. And that way I can rough in a nice curve like this, that is sort of roughly to scale. Now to look at the other example, y equals 2 lots of tan x over 3. Now this could be written a bunch of different ways. It might be written as a third x, and that would mean the same thing, wouldn't it? So the number that's sitting virtually sort of in front of our x, or the number of x's we've got here, is a third. So as we go to think about what the amplitude and the period of this graph are, well, we're using tan, so the whole idea of amplitude doesn't really come into play. We have stretched our graph, so it's twice as tall, if you like, But since it goes on to infinity and down to minus infinity, that concept of amplitude is not really relevant. I thought it through, went, no, not going to need that. I do need to think through the period though. Tan normally has a period of pi over n, n being whatever the number is, however many x's I've got. So what I've actually got here is pi over a third, and that's the same as 3 pi. So that means to get one cycle done and repeat upon itself again, it'll do that every 3 pi rather than every pi. So again, a little rough sketch helps me here. We need to just sketch it for one period. So think about what you know about the normal tan curve. Normally it sits about the origin like this. It's an odd function. And its normal width before it repeats again is pi. And if it's got half of its period out this side and half out this side, that makes this normally pi on 2 and minus pi on 2. And if it's got a period of pi, normally it would go through 0. The next place it would go through out here would be pi. So it's repeating every pi. Now this rough sketch helps me think through what I'm going to have to draw for my good sketch, because instead of this being pi, it's now going to need to be 3 pi. So I can virtually just label this on my little rough sketch. If that's 3 pi, then I'm going to need this asymptote to be halfway between the two. And I can start to draw it out now and think, well, it's going to start at the origin still, even if I've stretched it vertically, that's not going to change that, or stretch it horizontally, it's not going to change that. But my key points then, it starts at pi, it's going to be having its next x-intercept at 3 pi. And my other point of interest, this asymptote is halfway between those two. So halfway between 0 and 3 is 1.5. Let's call that 3 pi on 2. That's where my asymptote will go. And now it's just a matter of putting in my rough shape. It comes up here, although that's not strictly part of the bit I'm going to draw, towards this asymptote, and then it comes up again. And if you want to, you could draw more of it there, but we only have to draw one period of it, so it makes sense to go from 0 till it repeats again. Now we have to tie in our scale somehow. So we've got our intercepts, we've got our asymptote, we need to label one other point. So it makes sense just to pick a point that you know what to do with and put it in. Now, thinking of tan of something that's nice and straightforward, maybe choose a point that's halfway along here. Let's go 3 pi on 4. Now, if x is equal to 3 pi on 4, and I just picked a random point here, I chose a point that would have a positive answer, then y is going to be, sub it in, 2 times the tan of 3 pi on 4 over 3. Now, if you're going to divide something by 3, that's the same as multiplying by a third, isn't it? So I can multiply it by a third like that. Okay, now the 3's cancel here, and what I've actually got is pi on 4. That's handy, because the tangent of pi on 4, that's tan of 45 degrees, that's 1. And so I've got 2 times 1, which is 2. So that means that this point here that lines up with this one would be, I've made a mess here on my graph, I'm going to rub out my working so that you can actually see my drawing, is going to be 2. And I've labelled that point to tie in the horizontal scale and the vertical scale.